Hello friends, welcome to the last lecture of the course Exploratory Data Analysis for Data Science with R software. So you can recall that in the last lecture, means earlier lecture, right, we had discussed about that how you can extend this EDA, the tools of EDA to the multivariate data, and we had discussed the concept of mean vector. And we had demonstrated it in the R software for row means, column means, row sums and column sums also. So it was a very simple and easy exposition for you to understand that how the tools of simple tools like as measures of central tendency can be extended to a multivariate data. Now, today in this lecture, we will continue on the same topic and we will try to see how the concept of variability and association can be extended to multivariate data. So you have seen that when we talked about the variation, we had talked about the concept of variance. And when we had two variables, then we talked about the concept of covariance. And we also used the concept of correlation coefficient. So in this lecture, I am going to combine the concepts of variance and covariance together, and then I will combine I will discuss the concept of correlation coefficient in the setup of a multivariate data. That how you can extend it, and the main part is how are you going to interpret it. And the third thing is this, how are you going to compute it in the R software, which is very easy. So let's begin this lecture and try to understand this concept. So we had understood in the last lecture that when we are trying to work in a say data science, usually there are more than two variables and we need to consider all of them together. So when we have only one variable, we represent it by suppose here x1 and we conduct the univariate analysis. And similarly, when we have two variables, we represent them say here x1 and x2 and we write both these variables in a 2 cross 1 vector and we conduct the bivariate analysis. So bivariate analysis has an importance that we study the role of x1 and x2 individually as well as jointly. Similarly, when you have three variables, we represent them say here x1, x2 and x3 in a 3 cross 1 vector and we conduct the trivariate analysis. Right. Remember one thing, as I said earlier, these vectors are not the data vector, but they are the vectors of vectors and matrices. And similarly, when we have more than two variables, say p variables x1, x2, xp, then we write them in the form of a p cross 1 random vector, say x, and then we write here underscore. And then we conduct the multivariate analysis. So I am not going to consider here the multivariate analysis tool, but I simply want to extend here the concept of variability through the covariance matrix. What is the covariance matrix? Let us try to understand it. So in the case of univariate analysis, when you have only one variable, say x1, then you consider only one aspect, variance of x1, say this is sigma 1 square. And now when you have suppose bivariate setup, then you consider the variances of x1 and x2 as sigma 1 square and sigma 2 square. So you have two variables, x1 has variance sigma 1 square and x2 has variance sigma 2 square, but beside this thing x1 and x2 together they also have a covariance and we represent this covariance between x1 and x2 as say sigma 1 2. So now there are three pieces of information. One is about the variance of x1, variance of x2 and say covariance between x1 and x2. All this information can be expressed in the form of a matrix which is called as covariance matrix. And you have to keep in mind one thing, that the covariance between x1 and x2 is the same as covariance between x2 and x1. So this sigma 1 2 is the same as sigma 2 1. So the next question is how do we write and how do we arrange them in the form of a matrix. If you try to see here, this x1 and x2 is a 2 cross 1 vector. So when we try to write it like this here, COV of this vector x1 x2, then on the diagonal elements we have the variances. So, on the first diagonal element, this will be the variance of x1, second diagonal elements variance of x2. And then on the off diagonal element, there will be covariances between x1 and x2 and x2 and x1, but which is same as the covariance of x1, x2. So, this is represented here as like this. On the diagonals, these are the variances, and on the off diagonal elements, this is covariance sigma 1, 2. So, this matrix is called as covariance matrix. So, this is if you try to see, this is a symmetric matrix. Why? Because covariance of say this x1 and x2 is the same as covariance between x2 and x1. Similarly, when you have say trivariate case, then what happened? Then there are three variables x1, x2, x3. x1 has variance say sigma 1 square, x2 has variance sigma 2 square, x3 has variance sigma 3 square, and then now x1, x2 has a covariance, say covariance between x1 and x2 is sigma 1, 2, which is same as sigma 2, 1. Similarly, covariance between x1 and x3 is sigma 1, 3, which is same as sigma 3, 1, and x2 and x3 has covariance between x2, x3 is sigma 2, 3 or say sigma 3, 2, which is the same value. Now, we try to combine all these variances and covariances in the form of a covariance matrix. And we write here the covariance of a vector x1, x2, x3, which is a 3 cross 1 vector in the format like this. The diagonal elements, if you try to see variance of x3. Now, the next one is here, the second column first row, or say first row and then second column here. This is covariance between x1 and x2. And then I have here covariance between x1 and x3. Right, first row, second column, and because this is a symmetric matrix, so this covariance of x1 and x2 is going to be the same as covariance between x2 and x1, and covariance between x1 and x3 is going to be the same as covariance between x3 and x1. And then finally, in the second row and in the third column, we have here covariance between x2 and x3, which is same as the covariance between x3 and x2 in the third row and second column. And all these values are expressed here in the form of like this one: variance of x1 sigma 1 square, variance of x2 sigma 2 square, variance of x3 sigma 3 square, covariance between sigma 1 2 and sigma 2 1, then covariance between x1 and x3 sigma 1 3 and sigma 3 1, and finally the covariance between say x2 and x3 sigma 2 3 and sigma 3 2, which are the same. So, if you try to see, this is a symmetric matrix, the off diagonal elements and in the upper and lower diagonal, they are the same. So, this is how we express all these terms in a covariance matrix. Now, similarly, if you are considering here the multivariate case, then the same story can be extended, that you have here variable x1 with variance sigma 1 square, x2 with variance sigma 2 square, xp with variance sigma square p. And then similarly, all pairs of these variables will have covariance. So, x1, x2 will have covariance sigma 1 2, which is same as sigma 2 1. x1, x3 will have the covariance sigma 1 3, which is same as sigma 3 1. x2, x3 will have the covariance sigma 2 3, which is same as sigma 3 2, and in general I can say that xi xj has the covariance sigma ij, which is same as sigma ji, and I is not equal to j, goes from 1 to p. Now, you have to write down all these things in the form of a covariance matrix. So, the same concept I try to extend it. So, the covariance matrix of a random vector x underscore is written as covariance of x1, x2, xp, which is a p cross 1 vector. And now, if you try to see here on the diagonal elements, we have here all the variances, diagonal elements, variances, and here off diagonal elements, they are the covariances. So, you can see here that the first row is like the covariances sigma 1 2, sigma 1 3, sigma 1 p, which is the same as the first column sigma 2 1, sigma 3 1 up to sigma p 1. And similarly, the second row will be something like sigma 2 1, sigma 2 3 and sigma 2 p, and this will be the same story in the off diagonal elements also. So, you can see here, this is how we try to arrange all the values, and the last row will be here sigma p1, sigma p2, sigma p3 and sigma square p. Now the next question is, how are you going to compute this covariance matrix in the R software? It is very simple. You simply have to use the same command which you used earlier for computing the covariance. But the only thing is this, now X has to be a numeric vector matrix or a data frame. Right? Earlier X was only a data vector, or there were two variables X and Y which were in the, and both were data vector, right. So now let me try to take the same example which I took in the last lecture and try to show you how you can compute this covariance matrix. So in that example, we had considered the 4 cars, car number 1, 2, 3, 4, and we had recorded the data that the car number 1 used 5 liters of petrol and covered 90 kilometers of distance. Car number 2 used 4 liters of petrol and covered 100 kilometers of distance. Car number 3 used 6 liters of petrol and covered 80 kilometers, and car number 4 used 7 kilometers and covered 125 kilometers of distance. So this data has been recorded into two data vector, mileage and petrol here, and based on which we have created here a matrix with 4 rows and row equal to 4 and col equal to 2 and data equal to from this data vector of mileage and petrol. So this car mat comes out to be here like this. So you can see here, this is here the matrix, and this is matching. If you try to write down here this matrix like this. So now if you try to see here, I try to use here the command here COV over the matrix car mat, right. So if you try to see, this is what you get. So the main thing here is you have to understand how are you going to read it. So this is here the first variable. So your first variable was here, say here mileage in the column you can see here, and the second variable was the petrol. So this is the variance of mileage, and the second diagonal elements is the variance of petrol, and the off diagonal element, this is the covariance between mileage and petrol, and which is the same as the off diagonal element 10.833, right. So this is how you can compute and can interpret it. And the same thing I try to do with the second example that we took in the last lecture, that we had recorded the marks of 20 students on, say, in an exam in which students have got marks out of 250, and we also recorded that the student has studied for how many hours in a week, and which was variable x1, then variable x2, that number of assignments submitted in a month, and then variable x3, number of hours of play in a week. And this data was stored here in this format. There the student number 1 has got 180 marks, the student studied for 34 hours in a week, and the student submitted 3 assignments in a month and played for 15 hours in a week, and so on. So this data on 20 such students was recorded, and we had converted them into a data matrix. And first we stored them in the data vector x1, x2, x3 and here y, and then we created a matrix of 20 by 4 order. So by writing n row equal to 20, n col equal to 4, data is equal to like cy x1, x2, x3, and we had the data. Now the main thing is this, when I am trying to operate here the operator COV over this data mat, then it looks like this. So if you try to see, these are our here variances on the diagonal part. So if you try to see your this data structure was y, x1, x2, x3. So this is here the variance of y, this is here the variance of x1, this is here the third diagonal elements is variance of x2, and the fourth diagonal element here is variance of x3. Then similarly in the first row second column, this is the covariance between here y and here x1. Then in the third row, the second row is covariance between y and x2, and then the fourth column here is the covariance between y and x3, and so on. And similarly if you try to go to the second row, so right, because this is a symmetric matrix, so this value in the third column and second row is the covariance between x2 and x3, and x2 and x1, x2, right. So best thing is to write down here. So this is here the covariance between, see here x1 and here see here x2, and then you have here the element here covariance between x1 and x3, right. Best thing is to write here y x1, x2 and here x3, so that it becomes easier for you to understand, right. And so similarly, if you try to see here, what is this value here? This is the covariance between x2 and x3 and so on. And the lower diagonal are the same as the upper diagonal. You can see here this same as like this is same here like this, and this is same here like this and so on. So this is how you have to interpret it, and this is the screenshot of the same operation. So let me try to show you these things on the R console so that you get confidence. So you can see here this, I tried to first create here the KANPUR-NPTEL data matrix. So you can see here this is here KANPUR-NPTEL, and then you try to find out simply say covariance of here KANPUR-NPTEL, right. So you can see here this is the value. It is very simple to operate. And now if you try to take here this data set, data matrix consisting of say y, x1, x2, x3. So this is your here like this, and now if you try to say here covariance of data mat, we can see here this is here the covariance matrix. Finding is very easy, but then the main thing is how do you read it and how do you understand it. Okay, so now after covariance matrix, I come to the concept of correlation matrix, right. So this concept is very, very similar to what you have done in the case of this covariance. Suppose you have two variables x1 and x2. So if you try to see x1 has a correlation with x1, which is always 1. x2 will also have a correlation with x2, which will always be 1. And x1 has correlation with x2, which I am denoting as R12. So now we can combine all this information in the form of a correlation matrix. So this will be here COR of x1, x2, which is a 2 cross 1 vector here. So the diagonal elements are always going to be the 1 because they are representing the correlation between x1 and x1. The second diagonal element will be correlation between x2 and x2, right. And the correlation between x1 and x2 is indicated here on the off diagonal element R12. So it is very easy. Similarly, when you are trying to consider a trivariate case, so there will be 3 variables x1, x2, x3. So x1, x2, x3 with them, the correlation will always be equal to 1, right. Now x1 has a correlation with x2, which is indicated by here R12. x1 has a correlation with x3, which is indicated by R13, and x2 has a correlation with x3, which is indicated by R23. Now we try to combine all this correlation in the form of a matrix. So the correlation of vector x1, x2, x3, which is a 3-column vector, will be a 3 by 3 matrix. So you can see here on the diagonals, this is correlation between x1 and x1, so which will always be 1. Similarly here, all the diagonal elements are going to be 1 because they are the variable, the correlation of the variable with itself. Off diagonal element, if you try to see, so in the first row there is R12, which is the correlation coefficient between x1 and x2, then correlation coefficient between x1 and x3 R13, and in the second row it will be R23, which is the correlation coefficient between x2 and x3, and this is a symmetric matrix. So this R12 will be same as R21, R13 will be same as R13, and R23 will be same as R32. So this is called as correlation matrix. And similarly, if you try to extend it for a multivariate case in general where you have p variables, so all the x1, x2, xp, the correlation of x1, x2, xp with themselves, mean correlation between x1, x1, correlation between x2, x2, correlation between xp, xp will always be 1, right. So the diagonal elements of a correlation matrix will always be 1. Now you have to look for all other correlation pairwise. So x1 has a correlation with x2 R12, x1 has a correlation with x3 R13, x1 has a correlation with say x4, x5, xp, and similarly x2 has a correlation with x3 R23, and so on. xi has a correlation with xj. In general, it is rij, I not equal to j, which goes from 1 to p. So now I try to combine all this information in the form of a correlation matrix. You can see here all the diagonal elements are the correlation of the variable with the same variable, which is always 1. Then in the first row You have the correlation between x1 and x2, which is R12, correlation between x1 and x3, R13, the correlation between x1 and xp, R1p, and second row the correlation between x2 and x3, R23, and similarly here the correlation coefficient between x2 and xp, R2p, and this is a symmetric matrix. So, this will be the same in the off diagonal elements also, right. So, this is how you can write down the correlation coefficient of matrix of cor and x underscore, that means random vector. This correlation matrix in our software can be computed by the same command CORX. Earlier, if you remember, we had used the command COR x comma y to compute the correlation coefficient between the values stored in two data vectors x and y. But now I am using x here as a numeric vector matrix or a data frame. So, CORX will give me the correlation matrix. If you already have found the covariance matrix, then there is a command here COV2COR, where 2 here is the number 2. This command will scale a covariance matrix into the corresponding correlation matrix efficiently. So, V is here a symmetric numeric matrix, which is usually positive definite, such as covariance matrix. So, I will try to show you the application of both the commands. So, I try to use here the same data set of the car and car's mileage and car petrol. So, we already have created the data matrix car mat. So, I try to use here the command here cor over car mat. So, if you try to see these diagonal elements are 1, because they are the correlation coefficient between mileage and petrol and petrol. The correlation coefficient between mileage and petrol is coming out to be here 0.434 and so on, which is the same on the diagonal off diagonal element. It is very simple to use. And similarly, because you already have obtained the covariance matrix, which I am trying to store as here V. So, V is now the covariance matrix of car mat. So, if you try to see, V is here like this, which you obtained earlier. If you try to use the command here COV2COR, then the covariance matrix will be translated into a correlation matrix, which is very easy, right. Now, I take here the second example, where we have collected the data on 20 students of their marks, number of hours of study, number of assignments submitted, and number of hours of play, right. So, in this case also we have got this data set, we had created the data mat here, this data matrix. So, now I simply use here the correlation coefficient, or I use the command here COR over this data mat. So, you can see here, this is here here y, x1, x2, and here x3. Same here y, x1, x2, x3. So, you can see here the diagonal elements are always here 1, right. And the off diagonal elements, if you try to see, this is the, if you come to the first row, so this is here the correlation coefficient between y and x1, this is the correlation coefficient between y and x2, and this is the correlation coefficient between y and x3, right. Similarly, if you try to see here, this is here the correlation coefficient between x1 and x2, and this is here the correlation coefficient between x1 and x3. And finally, we have here, this is here the correlation coefficient between x2 and x3. And yeah, this is a symmetric matrix, so you can see here these values are the same, right, and go on here. So, they are the same matrix, this is symmetric matrix, and this is here a screenshot of the same operation. And now, if you consider the second command COV to COR, it is very simple. You save the covariance matrix of data mat as V, which is here like this, and then you use here the COV to COR over V. So, this is here the correlation matrix, which is the same matrix which you have obtained here, right. And this is here the screenshot of the same operation. So, let me try to show you these things on the R console actually, right. So, we already have actually stored the data here. So, I do not need to do much actually here. So, if you try to see here cor of CAR mat, it is here like this. And in case if you try to use here this here V as here COV of CAR-MAT. Then you can see you are trying to store the data, and then if you try to use the command here COV to COR and here V. So you can see here this is the value which you have obtained. Right. Similarly, if you try to see, this is your here data mat. So if you try to see here the correlation of this data mat, it is here like this 4 by 4 matrix. And if you try to save the covariance matrix of this here data mat as here capital V, so capital V here is like this. And if you try to use the command here COV to COR for this data mat, right, you can see here, yeah, it has to be actually V, not the data mat. So COV to COR of here V. So you can see here this is the correlation matrix which you have obtained here very easily, right. So you can see here this was a very simple lecture, but my objective was to explain you how you can extend the concept of covariance and correlation along with variance to this concept of covariance matrix and correlation matrix. It was not a very difficult thing, but the more important part here is how you are going to take the conclusion from this matrix. Usually when we are working in a multivariate setup, we are interested in the joint say effect. But when you are trying to look at this covariance matrix and correlation matrix, they are trying to give you the pairwise information, 2 variables at a time. Just the only thing is this, all the correlation coefficient, all the covariances, variances, they are combined at one places. So yeah, many times it requires some experience and practice to understand these value, what they are trying to tell you. But definitely it comes by practice. It is not difficult at all. It comes by practice, and I wanted to just give you this idea that how you can extend the concept of a univariate to a multivariate setup. So my request to you will be, you please try to have a look, try to practice it, try to understand the concept, because this will be used at many places in the data science. So with this lecture, I come to an end to this course also. Thank you very much for your patience listening to me, and I hope this course is going to be useful, beneficial. I am not claiming that by this course I have converted you into a data scientist, but definitely I have created the foundations on which you can become the data scientist. Whenever you are working in data science, the data size is huge, data is coming continuously, and it is stored in different types of formats, and usually the person who is handling the process or the experiment, they only have the wish, I want to know this thing. Beyond this, usually they don't know. It is the job of statisticians and data scientists to understand their requirements, what they want to do, and then they have to think what statistical tool they have to use so that they can get the information which the experimenter wants. And usually in the data science, the data will be coming from different types of subjects, right. So it is not necessary that as a data scientist you have to be good in all the subject, but you must have a capability to understand what's happening in the process, for which I think, in my opinion, you need to spend some time with the experimenter, try to understand, try to ask different questions, try to translate the questions for which you need an answer into a simple language which my experimenter can understand and can give us the better information. And over a period of time, if you practice more, definitely practice is very important, experience is very important to work to become successful as a data scientist. This is very important. Sometimes very small, simple tools also does magic. They give us very important information hidden inside the data. And I always said that data cannot speak. This is only you who is going to use different types of tools to understand the language of the data and to dig out the information which is contained inside the data. For that, it is your choice whether you use graphical tools, whether you use analytical tools, whether you need both of them, or you use a tool which I have taught you, or you may have to study it yourself. But without understanding these tools from the fundamentals, you will possibly not be able to reach to the depth and to the point what experimenter wants. So once again, my advice to you is that as a data scientist, I know that you all will have a great future, but this society and this country expects a lot from you at this moment. So please try to practice, please try to understand this concept. They are not difficult, and I am confident that you will become a very good data scientist. So may God bless you, and we will see you sometimes somewhere once again. Till then, goodbye.